Hi, and welcome to TEMEKO. In this video about Lagrange's method, we continue from where we left off in the last video. During this video, we are going to learn the other method to form the equation of motion, that is an energy-based method. We call this method the Lagrange's equation method. In addition to learning how this can be used, we are also going to discuss some of the benefits and drawbacks related to both Newton's and Lagrange's method, so that you can choose a suitable method to be used for different problems. Let's get started. What is Lagrange's method? Well, the main difference here compared to the Newton's method is that in the Lagrange's method we are going to calculate the work done by the system while trying to find the difference between the system's kinetic and potential energies. L equals T minus U. This will eventually yield the system's equations of motion for us. Now that you have a basic idea what Lagrange's method is all about, let's go through the steps to find the equations of motion for the same multiple degrees of freedom system that we used in the previous video by using our new method. The first thing to do in this procedure is to select a generalized coordinate for each moving body in the system. Usually, a distance, angle, or other type of coordinate can work as a generalized coordinate so long as it defines the position of the body uniquely at any time. In our system, we can choose the distance xi moved by each of the three bodies to be a generalized coordinate. Thus, we will have three separate generalized coordinates which we are going to also designate by the letter qi. Okay, now that we have our generalized coordinates selected, what then? How should we proceed? Well, the next step is to derive kinetic and potential energy equations for our system in which we include all our chosen generalized coordinates as shown. After this is done, we can derive our group of equations of motion by using Lagrange's formulation, which can be written as d dt of delta t delta qi dot minus delta t delta qi plus delta u delta qi equals capital Qi. I equals 1, 2, 3, etc. till n, where T is the kinetic energy and U is the potential energy of our investigated system, whereas capital Qi contains the generalized non-conservative forces defined with the help of virtual work and virtual displacement, which we can express as follows. Capital Qi equals delta W delta Qi. Yeah, I know what you're thinking. It seems like it's time for a coffee break, so let's get some coffee and then come back. Okay, we're back, or at least I hope most of us are, and nobody got spooked by the Lagrange's formulation. It's not as scary as it looks. To relieve your worries, let's go through it together to see how to apply this formulation and how it's quite easy to solve. Firstly, we should partially derive both the kinetic and potential energy with respect to each of our selected generalized coordinates. This should not cause any gray hairs because we're already masters at this. After this step is done, we should use the principle of virtual work to find the set of generalized non-conservative forces that are affecting each of the bodies in the system. The trick here is to understand what is meant by virtual work. Basically, we can consider virtual work as the amount of work that is done by an external force or moment to deform the object only by a minimal amount. We call this minimal deformation as virtual displacement because it's so small that it's not really measurable in the real world. Well, if it's not measurable, then why do we even bother to talk about this principle, you may ask? That's a good question. Actually, we are using the principle of virtual work to map the two types of coordinate systems together. See, if we have defined forces in another coordinate system rather than the generalized coordinate system, we can map or translate these forces into our chosen generalized coordinates easily by using the virtual work principle. This is very useful in cases where we could have generalized coordinates that might be combinations of length and rotation displacements, such as in the case of a simple pendulum. Luckily for us, in our example system, we are dealing only with one type of displacement, which makes the mapping unnecessary at this time. So our generalized non-conservative forces for each of the bodies will become Q1 equals delta W delta Q1 equals F1T delta Q1 delta Q1 equals F1T. Q2 equals F2T and Q3 equals F3T. After we have applied Lagrange's equation for each of the bodies in the system, we can assemble and form our system of equations of motion into matrix form, just like we did in Newton's method. As you can see, the equations will be the same regardless of the method used to form the equations of motion. The main difference between these two methods is, however, how easily we can apply them to solve equations of motion for different types of systems. Usually, if the system consists only of one type of generalized coordinate, then we prefer using Newton's method because it's not as mathematically demanding as Lagrange's method. On the other hand, if we would like to analyze more complex systems which consist of different types of generalized coordinates, then Lagrange's method is more suitable because it can map coordinates together by using our presented mapping tool. So deciding which method to use depends solely in our system's complexity. Most often, Lagrange's method is more usable because most of the dynamic systems that we analyze in real life are complex by nature. Now you should have a good grasp on the differences between the two presented methods to form the equations of motion. Hopefully, now you know the procedure related to Lagrange's method and you are also aware of which principle it's based on. Thank you for watching and have a nice day.